Hello everyone, welcome to my video on properties of limits. In the last video we saw an introduction to limits and the notation. Now we're going to be looking at certain properties that we have to apply, and we'll take a look at a couple of examples. So first of all, let's consider two functions f and g whose limits exist, and the notation we write is the limit of f of x as x approaches a is equal to some number L, and the limit as x approaches a of g of x is equal to b, where a, c, l, and b are all constants. They belong to the set of real numbers, and we have the following properties. So the first property is called the constant law. Let's write that down. Constant law. And the property is the limit as x approaches some number a of a constant c. What is that equal to? Well, this is saying that x tends to a, but if you're considering just a constant, then this will always be c. Essentially your x is being replaced by a, but in the constant there's no x, so we leave it as c. In a sense, we could think of it as a function y equals y and x. If you have to graph a constant function, it's just a vertical line at whatever number that is. And no matter what x values you choose, it's always going to hit, your y value is always going to be c. And this is what the constant law tells us. Okay. If we look at an example, just a quick example, this is the property. An example of this would be, let's take the limit as x approaches 2 of 6. Well, x is approaching 2, but the constant function is always 6, so the answer of this limit would be just 6. Okay, let's take a look at other properties. So property number 2 is called the identity law. And the property is the limit as x approaches a, some value a, of x is equal to, well, x is being replaced, or x tends towards a, so x is being replaced by a, so just a. Okay, so this is our second property called the identity law. If we consider an example, the limit as x tends to 3 of x is equal to, well, you're essentially just replacing your x with 3, so this gives us 3. This is the identity law. Next we have, I'm going to combine two of them. We call them the sum and difference. I won't prove these properties, but maybe in a future video I'll consider to prove them, maybe in advanced analysis or something. For now I'm just going to state them. So we have the sum and difference law, which states that the limit of the sum or difference is equal to the sum or difference of the limits. The way we state it is, well, the way we write it is limit as x approaches a, I'll put them in brackets, f of x plus or minus g of x, it doesn't matter, is equal to, what we're essentially doing is we're separating. We're taking the limit of each term individually. So instead of taking the limit of the whole thing, we're just going to take the limit of f and then add it or subtract it to the limit of g of x. Okay, so we're taking the limit of each term individually. That's the sum and difference law. Let's take a look at an example, something like, if we take the limit as x tends to 2 of x plus 4. So what we're doing here is we're taking the limit as x tends to 2 of the x and the 4 individually. So this is going to be x plus, I'm going to rewrite the limit as x tends to 2 of 4. And on this piece here, limit as x approaches 2 of x, this we're applying the identity law up here. So we're essentially just substituting the x with the value it's approaching with. So in this case here, it's approaching 2. So this value here is equal to 2 plus, and the limit as x approaches 2 of 4 is the first property that we saw. So since there's no x's in this constant 4, the limit as x tends to 2 is always just 4. And now we sum them. 2 plus 4 is 6, and that's the answer. Okay. Same thing, if we would have put a minus sign, we would have done the same process here, and this would have been 2 minus 4, which would have given us negative 2. Okay, let's take a look at other properties. So the next property is called the constant multiple law. And we could write it as the limit as x approaches a of some constant multiplied by our function f. And essentially what we could do is take the constant and remove it from the limit, or take the limit of just the function. So the constant right now is inside the limit, we could pull it out, constant times, and then we could just take the limit as x approaches a of f of x. This is commonly used, and let's look at an example of what we mean by the constant multiple law. So for example, if we're trying to find the limit as x approaches, let's put 4 of 5 times x, essentially what we're doing is we're taking out the constant 5, we're going to pull it on the outside, 5 times, and then we'll take the limit as x approaches 4 of x, and now we're applying the identity law. So since we're taking the limit as x approaches 4, we're replacing x with 4. We're essentially substituting it, giving us 5 times 4, which is 20. Okay. So this is the constant multiple law. Let's take a look at another. So now we're at law number 5. This is called the product law for limits. Okay, so essentially if we have the limit as x approaches a of a product of functions, so let's put f of x times g of x. So we're multiplying two different types of function, or sorry, two different functions. Then what we could do is take the limit of each function individually. So we'll take the limit as x approaches a of f of x, and then multiply that answer with the limit as x approaches a of g of x. Okay, so this is our property. And let's take a look at an example. So an example would be this might be a bit advanced, but I think it's okay. We'll take the limit as x goes to 0. And the two functions we're going to work with, they're continuous, so it's okay. We'll see this maybe later on when we see the direct substitution property, but essentially what we have is, let's take e to the x times cos of x. You want to evaluate this limit. We have a product of two different functions. What we're going to do is deal with each function individually. Take the limit as x approaches 0 of e to the x times the limit as x approaches 0 of cos of x. Okay. And at this stage here, what we're really using is the direct substitution property. This is something which I'll explain a bit more in details later, because this only works when you have continuous functions. But essentially what you're doing is you're substituting, or you're replacing your x with 0. So here, instead of e to the x, when we take the limit as x tends to 0, what we really have is e to the 0 times, and on this side, the limit as x tends to 0 of cos of x. You're essentially replacing the x, or you're substituting the x with 0 to evaluate it. So we have cos of 0. So e to the 0 is 1 times cos to the 0, also 1. You have to know your unit circle. 1 times 1 is 1, and that's the answer. Okay, so let's move on to the quotient law. So the quotient law is similar to the product law. So quotient meaning division, so we're dividing our limits. So we have the limit as x approaches a, and we have f of x, which is dividing g of x. What we're going to do is essentially take the limit of the numerator and take the limit of the denominator simultaneously. So we have the limit as x approaches a of f of x, all that divided by the limit as x approaches a of g of x. Okay, so the only restraint that we have here is that the denominator cannot be 0. So let's state that. Because in math we cannot divide by 0. G of x does not equal 0. So we just have to be careful for that. And this is the property. Okay, so let's take a look at a couple examples. We have the limit as x approaches, okay, let's do -2. I have zero. Let's change it. Limit as x approaches 0 of, let's do sine of x over, let's bring back e to the x. E to the x squared. Let's make it complicated. Okay. So taking the limit as x approaches 0 of sine x over e to the x squared, what you're going to do is take the limit of the numerator and then take the limit as x approaches 0 of the denominator. We have to ensure that the denominator is not equal to 0, but since it's exponential, it can never be equal to 0, so we're okay. And now we use the direct substitution property. So we're essentially taking the limit as x goes to 0 of sine of x. We're substituting the x with 0. So we're on the numerator we have sine of 0, and on the denominator we have the limit as x approaches 0, e to the x squared. So it's going to be e to the 0 squared. Okay. Notice that now that I substituted the limit, we do not write it anymore. So that's done. And on the top, sine of 0, again from the unit circle, we get 0. And e to the 0 squared is really just e to the 0, because 0 squared is 0. And e to the 0 is 1. 0 divided by 1 is 0, and that's the limit. Okay, so this is an example of the quotient law. We have a couple more laws to look at, and then we'll look at some examples. So the next property that we have is the root law. Which states that the limit as x approaches a of the root, let's put the nth root, it doesn't matter, the exponent of f of x is equal to the, what we're essentially going to do is take the limit and jump inside the root. This is one of the nice properties that we have for limits. We actually have a stronger statement, and this is true for any continuous function, but at the end of the day, the root law tells us that you could take the limit, jump inside the root, and evaluate the limit inside. Okay. We use this often in Cal 1. So the limit as x approaches a of f of x. Okay. So this is the root law. An example would be the limit as x approaches 2 of, let's put the nth root of x squared. So this is telling us that we could take the nth root of the limit as x approaches 2 of x squared. And in here, maybe not x squared, let's change it to just x, because we haven't seen squared. We'll leave it at this. And over here we're using the identity law. So we're essentially substituting the x with 2, giving us the nth root of 2. And that's our answer. Okay. So this is the root law. Next we have the last law, 8. This is the power law. Same idea. So instead of having a root, which by the way we could also write as, we could think of this as f of x, the nth root is the same thing as f of x, some function, all that to the exponent 1 over n. That's one of the properties of roots. You can rewrite it as an exponent. And that leads us to the power law, which is essentially the same thing. We're jumping into the power. So we're going to have the limit as x approaches a of f of x, some function, all that to the n. And what the power law says is that we could jump inside the exponent, giving us the limit as x approaches a of function f of x, all that to the n. Okay. So this is our property. And let's take a similar example. The limit as x approaches 2 of the, let's take x to the n, is the same thing. We're going to take the limit, jump inside the exponent, giving us the limit as x approaches 2 of x, all that to the n. And inside here we're using the identity law. So we're substituting the x with 2, giving us 2 to the n. And that's the answer. Okay. So let's take a look at a couple of difficult examples. Okay, so in this example here, we're asked to evaluate the limit, and on top of it, we have to justify our steps. So we have to state which limit law we're using. So we're given the limit as x approaches -2 of 5x squared plus x minus 7. Again, take a moment, pause the video, try it on your own, unpause, and then see if your answers matches mine. Okay, so the first thing we're going to do is we're working with a polynomial here. So what we want to do is take the limit of each term individually. So here we're going to be using the limit as x approaches -2 of 5x squared plus limit as x approaches -2 of x minus the limit as x approaches -2 of 7. Okay. We're allowed to use this because of the sum and difference law for limits. So by sum and difference, it allows us to take the limit of each term individually. Great. The next step, what I see is there's a coefficient of 5. Let's take the constant and pull it out. So 5 times the limit as x approaches -2 of x squared plus the limit as x approaches -2 of x, and the rest will leave. Okay. So all we really did here is take out the 5, and we're allowed to do this by the constant multiple law. And now for the first term, let's evaluate the limit using the power law. So we're taking the x and we're essentially substituting it by -2. Here we're taking the limit as x approaches -2, and here the function we have is just x, so it's essentially the identity law. So we're replacing the x with -2. And then lastly, we're taking the limit as x approaches -2 of 7. 7 is a constant. X is going to -2, but there's no x's here. So we're left with just -7. Okay. So here what we used were 3 different laws. We used the power law. We used the identity law. And we used the constant law. And don't get confused with the constant law and the constant multiple law. Okay, so the constant law, there's no x's involved. The constant multiple law is you have a coefficient which you're pulling out in front of the limit. Okay, and now we could evaluate the limit. So we get 5 times -2 squared. This is 5 times, be careful, this is 5 times 4. Don't forget to put your bracket. -2 squared is +4, plus -2, which is just -2, minus 7. So what we have here is 20 minus, and here we put 20 minus 9, and that gives us a final answer of 11. Good. Let's look at a harder example. So part B, this example here, we have the limit as x approaches 4 of x squared minus 6, all that divided by x squared minus 3x plus 5. So we begin by noticing that we have a quotient. So we're using the quotient law. We're going to take the limit of the numerator and the denominator individually. Let's do that here. Limit as x approaches 4 of x squared minus 6. All that over the limit as x approaches 4 of x squared minus 3x plus 5. So this is by the quotient law. Next, we're going to take the limit of each term individually using the sum and difference property. So we're taking the limit as x approaches 4 of x squared minus the limit as x approaches 4 of 6. I already took into consideration the negative, so here it's just 6 over the limit as x approaches 4 of x squared minus the limit as x approaches 4 of 3x plus the limit as x approaches 4 of 5. Of 5. Okay. And the property we used here was the sum and difference. So by sum and difference, law. Okay. And the next property that we're using is on the denominator here, we could pull out a 3. So let me just do that at the same step here just to save on space. So we're just going to take the 3 and pull it out in the front, and we'll add that we used excuse me, the constant multiple law. Okay, so we'll just take the 3 out and put it in the front. So negative 3 times the limit as x goes to 4. And here we're going to use the power law, and we're going to use the identity law here on the 6. So this gives us the quotient. We have 4 squared minus 6. And on the bottom here, we're using the power law again, giving us 4 squared. Over here, we're using the identity law, limit as x approaches 4 of just x. So we have minus 3 times 4. And over here, we're using the constant law. So limit as x approaches 4 of just 5 remains as 5. So just plus 5. So let me just squeeze it in up here. So what we used was by power law, identity law, and lastly we use the constant law. Okay. And now we just evaluate the limit. So 4 squared minus 16, 4 squared minus 6 is 16 minus 6, which is 10. And on the bottom we have 4 squared 16 minus 12 plus 5, giving us 4. This is going to give us 10 over 9. And that's our answer. Okay. So I hope you got the same answer. If you didn't, I hope you caught your mistake and you learned from it. The following property that we have here is the direct substitution property. We've actually seen this already and we've applied it in a previous example. The direct substitution property states if f of x is a polynomial or a rational function and the number a lies in the domain of f of x, then we have the limit as x approaches a of f of x is equal to f of a. So we're essentially just substituting whatever x is approaching into our function. And this only works if you have really we need the notion of continuity, which we haven't seen yet. We'll see in a future video. But right now let's work with polynomial functions and rational functions. So an example of this would be, let's say they ask us to evaluate the limit. So evaluate, and they do not state to justify. So last examples we saw, they asked us to justify each step. Here they're just asking us to evaluate the limit. And they give us the limit as x approaches, let's take 1, and we have 2x squared plus 6x minus 3 over 4x squared plus 1. Okay, so we don't have to apply the quotient rule. The direct substitution property allows us to just directly substitute our x into our function here. This is our rational function. So what we're essentially doing is we're substituting all our x values as it approaches 1. So we're replacing all the x values with 1. So this is equal to 2 times 1 squared plus 6 times 1 minus 3 over 4 times 1 squared plus 1. And this is a lot quicker than having to state and take the limit of each term, apply the quotient rule, the sum and difference property, the constant multiple law. Direct substitution just allows us to evaluate the limit immediately. So by plugging in whatever x approaches, and this gives us 2 plus 6 minus 3 over 4 plus 1, giving us 8 minus 3, which is 5, 4 plus 1 is 5, and this is just 1. Okay, so I'll give you a moment to try this problem on your own. We're taking the limit, so we're asked to evaluate the limit as x approaches -1, and we're given this function, x squared plus 1 all that cubed multiplied by x plus 2 all that to the 6. Okay, so pause the video, try this on your own, and see if your limit is the same as mine. So we're doing the direct substitution property, so we're essentially substituting x with -1, giving us -1 squared plus 1 cubed times -1 plus 2 all that to the 6. -1 squared, be careful, that's positive 1. This gives us 2 cubed times 1 to the 6. 2 cubed is 8, 1 to the 6 is 1, so we have 8 times 1. So you should get an answer of 8. Okay, let's keep practicing. Okay, so in this example here, we have the limit as x approaches 1, and we have this polynomial, x squared minus 1 divided by x minus 1. Let's evaluate it using the direct substitution property. So let's plug in x equals 1. What we get is 1 squared minus 1 over 1 minus 1. 1 squared is 1, so what we get is 0 over 0. This is a special case, so if you wrote that the answer is equal to 0 when we're done, that's incorrect. This is not equal to 0. 0 over 0 is something what we call an indeterminate form. Okay, we're going to see a lot of this later in the semester, or later on when we do L'Hopital's rule. But for now, there's two types of indeterminate forms that we have to know about, because the direct substitution property doesn't always work. This is a case where it doesn't work, where the denominator gave us 0. It's not essentially continuous on the domain, or the limit, we're evaluating the limit where there's a discontinuity. So this gives us the indeterminate form 0 over 0. We have to keep analyzing, and we have different tricks that we can use to analyze. The other type of indeterminate form that you have to know, so let's write this down, indeterminate forms. The two main types that we're going to work with for now is 0 over 0, 0 divided by 0, so we cannot divide by 0, so that's an indeterminate form. And the other type that we're going to see is infinity over infinity. So infinity divided by infinity is not necessarily 1, 0 divided by 0 is not 0, it's not 1, we don't know. We have to analyze the functions. Okay. So let's take a look on how to evaluate when we're dealing with limits that give us indeterminate forms, 0 over 0 or infinity over infinity.